see quantum gates. So these are basically the logical transformations that you can perform on qubits. Yeah, so recall that in the classical case, in classical computing, there were essentially only two non-trivial single-bit logic gates, right? So it was the identity gate, which lives, sends the 0 bit to 0 and the 1 bit to 1, and the NOT gate, which flips the bit, sends 0 to 1 and 1 to 0. Now, the situation is very different for the case of a single qubit. Now, why is that? Well, actually, let me start by asking you, so how many non-trivial sort of single qubit transformations do you think there are for qubits? A couple of people saying infinite, 4, 6. Man, there's a lot of difference between these extremes. Yeah, there are a lot. There are infinitely many. So recall that the general state of a single qubit is a vector, right? We can write it as, vector alpha beta. We also write it sometimes as, psi, which is alpha 0 plus beta 1. And alpha and beta obey these constraints. Magnitude squared sum to 1. So this means that the vector has norm 1, right? Just to remember, the magnitude of this vector is 1. That's another way to say it. So there are infinite possibilities for what the state of a qubit could be. It's not just 0 or 1. I mean, you can literally tell me, basically any, at least one complex number, alpha, right? You still have some freedom to choose beta. I mean, there's one constraint, but there are still infinitely many possibilities for beta as well. So definitely infinitely many possible states of qubits. And there are also infinite possibilities for what this qubit could be transformed to. So definitely the number of possible single qubit gates is infinite. So that's one thing to keep in mind. So here is how quantum mechanics postulates that states evolve. So yesterday we've talked about measurement and Born's rule. So that's one way that quantum states can evolve. So you can think of a measurement as kind of a more abrupt evolution, in which you typically, collapse the wave function, get classical outcome in return. And the second way that quantum states can evolve is via a linear transformation. So via multiplication by a matrix. So this is basically exactly what you've been, trying to understand all morning. Okay. So there will be chance to practice, what you've seen this morning. There's plenty of opportunity to practice. So there's just one additional condition on the matrix, which is that the matrix should be unitary. Now, don't worry about the word unitary itself. I mean, the additional constraint, I'll just ask you to tell me. I think Eric was already kind of hinting at it. We'll get to it in a moment. So now let's just quickly recall from Eric's lecture. You've seen that multiplying a matrix by a vector results in another vector. Here is an example where the vector 1, 0 gets transformed to 1, 1. And in particular, as as Eric told you, this transformation described by a matrix is always a linear transformation. It satisfies some very natural properties. So the one axiom you have to remember is a single qubit quantum gate is specified by a 2x2 matrix. It transforms the state of a qubit, which is a 2-dimensional complex vector with norm 1, into another state of a qubit via matrix multiplication. That's the one most important axiom you should take away from this lecture. So here's an example, which we have already seen, but with different language. So now let's go through it again. So one very common single qubit quantum gate is called the X gate or Polyx gate. It's also sometimes called the NOT gate. It transforms state psi, alpha 0 plus beta 1. You can represent it as a vector like this. It transforms it into this psi prime here, right? And if you compute the multiplication of the matrix X with the vector of psi, you will see that all that is happening is that, you know, alpha and beta are getting flipped. Okay, so essentially what this NOT gate does is it flips the zero sort of vector to a 1 vector, ket 0 to ket 1, and it transforms ket 1 to ket 0. So it's kind of like the quantum analog of the NOT gate that we had classically. Does that switch the probabilities too? Yes, yes, absolutely. So the vector before the X gate was alpha 0 plus beta 1, right? And after you apply the gate, it becomes alpha 1 plus beta 0. Or beta 0 plus alpha 1, but that's the same vector, right? Beta 0 plus alpha 1. You know, the addition is commutative, so you can rearrange the order. So yes, so the probabilities of the 0 and the 1 get flipped. So it will collapse to 0 after applying X. If you were to measure it, it would collapse to 0 with probability beta squared, modulus, the modulus in Bohr, yeah, modulus of beta squared, yes. Correct. So it's the quantum analog of the flipping the bit. You're turning the 0 bit in the ket 0 into a ket 1 and the ket 1 into ket 0. Now, of course, it doesn't just do that, right? It doesn't just act on, you know, the ket 0 and the ket 1, right? Importantly, you know, you can sort of, okay, let me back up. So how does it act on ket 0? It turns it to ket 1, right? How does it act on the qubit state ket 1? It turns it to ket 0. But of course, it more generally sort of extends by linearity to any sort of qubit state, alpha 0 plus beta 1, and X in this way here, as it's written. Okay, so we can specify it by deciding, you know, what it's going to do on the standard basis elements, right, on 0 and 1, and that already specifies how it's going to act on any other generic qubit state. Okay. Okay, so now let me tell you about unitarity, right? So not all linear transformations, not all matrices map valid qubit states to valid qubit states. Anyone can tell me why is that? Yeah, Kieran, that's correct. So the magnitude, you know, of the new vector after the transformation, exactly, yeah, it's not necessarily 1, right? So this is a constraint that we have to add. Yes. So valid quantum gates must map vectors with norm 1 to vectors with norm 1. This condition is called unitarity. And now I'll tell you a condition on matrices, which, you know, makes them, you know, if and only if they are they're unitary. But, you know, I won't tell you how this condition is derived. You can sort of take it as a given. So unitary matrices are precisely those matrices U, such that, you know, when you multiply U by this matrix U dagger, okay, U dagger is obtained from U by taking the complex conjugate of every entry and just transposing the resulting matrix. So when you take the product of U and U dagger, this is equal to the identity. Okay, so unitary matrices are precisely those matrices U that satisfy this condition. But don't worry, we won't see how this is derived. All that you have to know is that, you know, the unitary matrices are the ones that map unit vectors to unit, you know, norm 1 vectors to norm 1 vectors. Okay, so all in all, a single qubit gate is specified by a 2x2 unitary matrix. But anyways, all that you need to remember is that it maps unit vectors to unit vectors. Like, you'll hardly ever use this UU dagger equals identity. Okay, So here are some examples of single qubit gates. Okay, so we've seen the NOT gate already. So first, the identity gate. So I'll tell you for each of these gates how it acts on the standard basis. Okay, because this specifies how it acts on everything else. So the identity gate maps the cat 0 to 0 and the cat 1 to 1. And so the matrix representation of the identity matrix is the following. Okay, and the way it acts on a general state is just it maps the same state to itself. Okay, the NOT gate, we've already seen it. It flips, sends the 0 cat to cat 1 and 1 to 0. Now, what about the Z gate? So the Z gate sends cat 0 to cat 0. So it doesn't do anything to 0, but it sends cat 1 to minus cat 1. So it applies a factor of -1 onto the cat 1 standard basis element. So if you want to see how it acts on a general state, alpha 0 plus beta 1, right, this will be turned into alpha 0 minus beta 1, right? And now the Hadamard gate is another very important gate. So the Hadamard gate is a little bit different than the ones before. So it takes 0 as an input. It sends it to an equal superposition of cat 0 and cat 1. So 1 over square root of 2, cat 0 plus cat 1. And it takes, the way it acts on cat 1 is it also sends it to an equal superposition of cat 0 and cat 1, except that there is a minus sign in front of the cat 1. Okay, so 1 over square root of 2 cat 0 minus cat 1. Where do these gates come from? Loa is asking. So how are they designed? So that's a very good question. So at the start, I told you that there, for single qubits states, there are actually infinitely many possible gates, right? Now, when you're doing computing, you want to be able, if you're thinking of practically implementing a quantum computer, realizing a quantum computer, you can't, sort of your hardware cannot possibly, be performing all sort of infinitely many gate. You can't possibly be, asking your hardware to right away apply, one of these any of these infinitely many single qubit gates. And you have to build any sort of algorithm from simpler building blocks. So these are what I'm showing you here, I, X, Z, H. They're very common building blocks that people use to design more complicated quantum circuits. Does that make sense? So people have sort of settled on the fact that these few single qubit gates here are, are very common and convenient as building blocks to build more complicated circuits. And so typically when people are trying to experimentally realize a quantum computer, they will show to you that it can realize this few gates and then other gates on multiple qubits. So, okay, then the Y gate, finally, the poly Y gate, acts on 0 by applying multiplication by I, and acts on cat 1 by applying minus I. And they also flip the 0 to the 1 and the 1 to the 0. So the poly Y gate is kind of similar to poly X, except that there's a factor of I for cat 0 and a factor of minus I for cat 1. Okay? Let me see, there are some questions here. Where does the 1 over square root 2 come from in the Hadamard? Yeah, so your So depending on what you mean by that, so you have to have 1 over square root 2 as opposed to, say, 1 over square root 3, if that's what you're asking, because the output vector after applying h has to have norm 1, right? So if you calculate, 1 over square root of 2 makes the norm of this output, 1 over square root 2, 0 plus 1, makes the norm precisely to be 1. So that's why you have 1 over square root of 2 as opposed to 1 over square root of 3 or pi or something. The probability. So here, okay. So maybe if I understand your confusion, so here there's no probability in the way that the gate acts. I'm literally right. I'm literally specifying to you, how it acts on each of the standard basis elements. I'm not talking, when I'm describing the gate, I'm not introducing any probability yet. I'm just saying, when you feed 0 as input to the gate, you'll get I times 1. When you feed 1 to the gate, you'll get minus I times 0. So here I'm not talking about, I'm not talking about probabilities. But yeah, I mean, if you input a 0, then after the application of a y, you get an I1, which means that if you were to measure the output qubit, there will be probability 0 of finding it in 0, and the probability would all be on 1, if that's what you're asking. So if initially, there was probability 1 to find it in 0, after you apply a y, by Born's rule, if you were to measure this state here that I'm highlighting, this I1, you with probability 1 find it as a 1, just by Born's rule. Is y a relative or a global phase change? It is a, well, what do people think? So that's a good question. So that's a good question. Actually, I'll turn it around to you all. So you all can answer Mikhail's question. Emily is asking her own question. She's asking relative. Yeah, so it is definitely a relative phase, because as you can see here, how y acts on the general state, right? It takes alpha 0 plus beta 1, and it maps this to I alpha 1 minus I beta 0. Okay, now I can always sort of pull out a factor of I. Okay, if I pull out a factor of I, the global phase doesn't matter, and I'm left with, alpha minus sort of I divided by I, which is minus beta, if I've done the calculation correctly. Something like that, okay? But anyways, it cannot be relative because there isn't a way to factor out. Yeah, so yeah, exactly. There isn't a way to factor out this phase and call it global. Absolutely, Fauzan, that's correct. In fact, I mean, if it were just a global phase, then remember that global phases are undetectable. So essentially, if this were a global phase, then this gate here would essentially be the identity. Like you can already see the fact that the Y gate is not applying just a global phase comes already from the fact that if you look at the Y matrix, right, it is not, it's not a multiple. I mean, it's, for example, it's not a multiple of X, it's not a multiple of the identity. If you were just applying a global phase, it would be a multiple of the identity. I mean, here it's also, for one thing, it's also swapping 0 to 1. And 1 to 0, okay? So it's definitely doing something. Okay, let's move on. So here's one exercise. We can do this one together, and then the others I'll leave for you to do later. So here the exercise is to apply the Hadamard gate to the state psi. There's an equal superposition of 0 and 1. What is the resulting state if you apply the H gate to this? Now let me show you again what the H gate does. So the Hadamard gate is very important. You see it coming up over and over. So it sends 0 to 0 plus 1, and it sends 1 to 0 minus 1. Yeah, Anjali and Jacob got it right. It sends it to 0. That's correct. You can do the calculation if it's not immediately clear to you. So, I mean, the way you apply H is you kind of apply it by linearity. You have H acting on 0, which splits it into 0 plus 1. And then you have H acting on 1, which splits it into 0 and minus 1. And you'll see that the resulting outcome is 0. We'll actually be seeing this calculation later again in a different form in this same lecture. Yeah, a bunch of other exercises. Okay, now let's get to the fun part of the lecture. So this actually, in my opinion, is one of the nicest parts of the course. So remember at the start, Jason told you a puzzle about a firework in a box. So where you had to decide whether a box that you cannot touch, you cannot shake, feel, or anything, whether the box is empty or it contains a firework. Okay, and the sort of catch is that the box, the firework is photon sensitive. Okay, which means as soon as a photon hits it, basically as soon as you look through one of the holes in the box to see if the firework is inside, you'll basically set off the firework. Okay, and the problem asks you to determine whether there is a firework or not by and at the same time without letting the firework set off. So this was the puzzle. And we had agreed at the start that a solution seemed impossible. I mean, by design, this problem is it's just meant to be impossible, right? If you look, you set off the firework, there's no way out. It turns out that there is actually a quantum solution to this puzzle. When I saw it for the first time, I was really quite stunned by this. So this is what we'll see in the next part of the lecture. So the quantum solution is given by this sort of physical circuit here, which we'll understand also from a formal point of view in terms of sort of quantum gates, etc. Okay, but the circuit looks like this. Okay, there is a source that fires a photon. Okay, then there are two mirrors. Okay. The mirrors are the ones that are drawn in blue. Okay, mirrors simply reflect any photon that hit them. Okay, then there are also two beam splitters, which are these items here in white. A beam splitter either lets the photon go through, okay, or it reflects it to go upwards in this case. And these two options happen with equal probability. And now at the very end of the circuit, there are two detectors. They are labeled with A and B, okay? And this simply record any photon that hits them. So Michal is already seeing ahead that the beam splitter is applying a Hadamard gate on the photon. That is correct. That is very correct. You're already seeing ahead. That's very good. So is the setup clear to, okay, so then let me just add one thing. The idea for this quantum solution is that you're gonna place the bomb, say in the bottom branch, in between the beams, the first beam splitter and this mirror at the bottom, okay? You're gonna run the circuit and somehow, based on where the photon lands, which detector it gets recorded at, you'll make your decision as to whether the box contains the firework or not. Okay. Is the setup clear for what are the components of this circuit? We'll get into a bit more details. Are the beam splitters polarized? I mean, they just emit a photon. The firework was already in the box. So here, here, okay, actually, oh, I wish I had the other picture. So the problem is exactly the same as before. So I'm either have a box that is empty or a box that has the firework. There are two holes in the box. I can look inside by sending a photon, but the minute the photon hits it, it will set off the firework if it's there. So I think it's the same problem as before, right?
Yeah, can I jump in?
Yeah, you can jump in, yeah.
So maybe go to the next slide real quick.
Mm-hmm.
So to be super clear, if the particle, right, if the photon is a classical particle, even with these objects, right, any fancy optics won't help, right? So we haven't like changed the problem by introducing new components, right? We will see how this really is a quantum puzzle solution by like the way that the beam splitter acts in the quantum sense. But if it was classically, it either let this tiny tennis ball go through, it still wouldn't have a solution. So
yeah, and also, yeah, that's a good point. And also, I mean, what I'm showing you here is part of the solution, not part of the problem. So, for the solution, you're allowed to do anything you want, right? The problem statement is on the slide before, where there are no beam splitters, there's no anything, right? Okay, so let me see. Okay, a photon is fired. Let's consider the case where there's no firework. Okay, so I'm placing, I wish I had that picture. So I'm placing the box right here in the bottom branch in between the beam splitter, the first beam splitter, and the bottom mirror. Okay, and now what I ask you to tell me is, when I fire a photon, what fractions of photons do you expect to land at detector A, and what fraction do you expect to land at detector B? So Loren is saying 50-50, Justin is 50-50, Miles is 75-25. Yeah, so actually in the 50-50, okay, so most people are agreeing with 50-50. So if there is no firework, then literally when I place the box at the bottom, the photon will hit the first beam splitter, with sort of half probability, it will go up. With half probability, it will take the bottom branch. Actually, I have this description here. And you see the sort of the GIF. With half probability, the photon will go up. With half, it will continue straight. The mirror simply reflects it. And once it hits the second beam splitter, half of the time it will go up, half of the time it will go down. If you compute, putting all of these things together, it is correct that 50% of the photon you would expect hitting detector A, and 50% would hit detector B. I'm also saying if there was a firework. Okay, so now, yeah, so now we're considering the case without firework. So this is what you would expect classically, okay? It turns out that this prediction is false if you're actually using a beam splitter. And this is because of what sort of Michal was already hinting at before. It turns out, right, as we have seen many times in the past few days, the photon is actually a quantum object. And as Michal was hinting at, the beam splitter is actually not doing this 50-50 split. It's actually a quantum gate. Okay. In particular, the beam splitter does not reflect half of the photons and sort of what I meant to say is, let the other half go through. Rather, the beam splitter puts, sort of an incoming photon into an equal superposition of being reflected and going through. Okay, and we can call this classical states of being reflected and going through as respectively cat 0 and cat 1. We can just give them a name, okay? But essentially, the beam splitter takes an incoming photon and puts it in equal superposition of going up and going through, sort of being reflected and going through. This is an illustration of how actually a beam splitter acts, okay? So if the photon is coming in sort of from the top part of the beam splitter, what happens next is that it's put in an equal superposition, 1 over square root of 2, of the state going up, being reflected, and 1 over square root of 2 of the state going through. Okay, we can call this two states here 0 and 1. And now if the beam splitter instead, if the photon instead comes from the bottom of the beam splitter, what will happen to it? It's still put in an equal superposition of going up, so through, and being reflected, but there is this extra sort of minus phase that appears, okay? This is how a beam splitter actually acts. Okay. So formally, what the beam splitter is applying is, if we call sort of the incoming photon from the top, we label that as being a 0. Okay, what the beam splitter is doing is it's turning 0 into 0 plus 1 over, not over 2, over square root of 2. I should say this is a typo here. Over square root of 2. Okay, so it turns 0 into 0 plus 1 over square root of 2, and it transforms 1, which we interpret as being a photon coming from the bottom, into 0 minus 1 over square root of 2. Yeah, why is the angle negative? So that's a very good question when it comes from a different angle, when it comes, say, from the bottom. So sort of ultimately, you can sort of build a beam splitter in the lab. Okay, this is what people do, and you don't know a priori how it's going to act. Okay, you set up, you build your beam splitter, you set up this circuit. This is what physicists did, and they observed, certain outcomes from this experiment. Meaning that the photon would land at detector A or B with some distribution. Okay, and then they had to come up with an explanation for the outcomes that they saw, and they realized that if they model the beam splitter as applying a Hadamard gate, and if they model sort of photon coming from down as 1 and coming from the top as 0, just like we did, then all of the observations from their experiments would be explained precisely and correctly. So it's not something that you decide a priori, right? So you build a beam splitter, you see how it acts, and it turns out that it acting as a Hadamard gate exactly matches what you see in the experiment. Does that make sense? But for the purpose of what we're going to see, think of the beam splitter as acting exactly in this way. And so let's revisit what happens to our circuit when we're still in the case of no fireworks being present. Okay, so the photon starts by coming from the top. Think of starting the photon in the state 0. After the first beam splitter, the state of the photon becomes 0 plus 1 over, again, should be square root of 2 here. So an equal superposition of being reflected upwards and going through. Now, and I'll show you a visual of this, but for now, let's go through the calculation. After the second beam splitter, the state will, sort of have a second application of Hadamard gate. So it will be H applied to this 0 plus 1 over square root of 2. And this is exactly the calculation that we did a moment ago in the exercise. Right? We're applying a Hadamard gate to 0 plus 1 over square root of 2. It's exactly the same calculation I showed you on the Jamboard. So after applying the second Hadamard gate, the beam splitter is uniquely in the state cat 0, which we interpret as being sort of entirely reflected. right? There's no amplitude at all after you go through the second beam splitter for the photon to be reflected. The photon will be uniquely in a state of going upwards, let's say, okay? There will be no amplitude on one of the other two directions, okay? So let's say that all of the amplitude is going up to detector A, and there's no amplitude for the photon hitting detector 0. So actually, let me show you in the case of no fireworks with an illustration. So this will be an example of interference. Let me show you here. So this is case 1 with no firework. The empty box leaves the photon unaffected. And now look at the GIF, right? You hit the first beam splitter, and now you're in this sort of ghost-like superposition. And by the time the two different branches hit the second beam splitter, and you know the additional Hadamard gates gets applied, you will have an interference, constructive for the ket0 component and destructive for the ket1. So what you observe actually at the end of this circuit is that your state is always going to be ket0. No amplitude on ket1. So only detector A is going to be hit. So the way we label, you know, detector A with ket0 or ket1, you know, going up or being reflected, that's not very important. So don't get too caught up into that, okay? That's just a labeling of things. The really crucial part is that if you start with a 0 and you apply two beam splitters, so two Hadamard gates, you end up at a 0. That's the important part. Whatever this label 0, this ket0 label means, whatever you make it mean, the important part is if you start with a 0, you end up with a 0. There's no amplitude on any other sort of classical state. So if you actually build this circuit in a lab and you were to run this exact experiment, you would see that the photon always hits detector A. So this is due to interference. If you see from this calculation, you know, the one amplitude interferes. There's the +1 here on the ket1, and there's a -1 phase on the ket1, which cancel out. Okay. So now what happens to our circuit when a firework is present inside the box? So Justin, in the example that we just saw, the box was empty. There was no firework, okay? And we saw that the photon always hits detector A. So now let's consider what happens when we do put a firework in the box, okay? So the key observation, so Miles is saying 75-25, which I think is a good guess. Let's see. So the key observation is that the firework acts as a measurement. It forces the photon to decide whether it has gone up or whether it has gone through. Why is that? Okay, so recall that after the first beam splitter, the state is 0 + 1 over square root of 2. We've applied just one Hadamard. Now, placing a firework in the box corresponds to making a measurement. You're asking the state, you know, were you 0 or were you 1? Did you take the upper path or did you actually go through? The reason why this is a measurement, and this connects to the discussions we've been having in the past days of what constitutes a measurement. A measurement is anything that extracts classical information from an experiment. In this case, the classical information is the firework. You hear the firework setting off and destroying the box or not, right? So if you hear that, if you see that the box is being destroyed, you know that the photon went through. If the box doesn't explode, then the photon must have taken the other branch. So in this way, you're definitely extracting classical information. You're forcing the photon to decide. So this is definitely a measurement. And by Born's rule, if we measure this 0 + 1 over square root of 2 state, with probability 1/2, the photon would have taken the lower path say corresponding to outcome 1, and the firework sets off. But with probability a half, the outcome of this measurement is 0, meaning the photon had been reflected, it has taken the upper path, and the firework does not set off. Okay. Now, in this second case, that the firework has not set off and the photon has taken the upper path, the question I have for you is, what happens when this photon that has taken the upper path reaches the second beam splitter? So I'm asking you to. So Justin is saying it interacts with itself like the double slit experiment. So right now I'm saying, there's one case in which, you're going below and you're setting off the firework. Okay, forget about that. And this the other case in which the box doesn't explode. Okay, now the photon goes up, and what happens when it hits the second beam splitter? Gives the same result as last time with no firework. Okay. Any other guess? So think about what we have done here, right? What Born's rule is telling us. So Emily is saying 50-50 of hitting A or B. Okay. Now remember what's happening here, right? So first beam splitter puts it into 0 + 1 over square root of 2. Then you're making a measurement, which means by Born's rule, you're going either up or through with probability a half. Now remember what happens, after you make a measurement. What happens to the state? It collapses, right? So the answer is that conditioned on the box not exploding. So if the box doesn't explode, the photon is going up. The new state of the photon, right? If we've gotten outcome 0, meaning taking the upper path, the new state of the photon is 0. It's ket 0, right? Because the state has collapsed to ket 0, since that's the outcome that we got. Right? This is remember that this is the rule of how measurements happen, right? They're subject to Born's rule, and the state after the measurement collapses to the outcome that you observe. So if the photon goes up, it means that the new state is ket 0. Okay, and so by the time the photon reaches the second beam splitter, Emily is right. There will be a 50-50 chance of hitting A or B. And this is because the second beam splitter applies, right after obtaining outcome 0, the photon has collapsed to the state 0. There is no longer any interference. And when we apply the Hadamard from the second beam splitter, we end up with an equal superposition of going through and being reflected. So we again end up with a 0 + 1, and so there's a 50-50 chance of hitting the first detector A or the second detector B. Right? To connect this with the double slit experiment, what we are doing here is exactly the case where we have an observer, in the middle, which sort of observes whether the photon is going through the left slit or through the right slit. And remember that when we have this observer, there is no longer any interference, right? The observer sees whether the photon is going left or right, and that collapses the wave function, and there's no longer any interference. This is exactly the analogy of what is happening here. You're making the measurement, collapsing the state of your photon to ket 0, and then when you apply H to ket 0, you're in an equal superposition of 0 and 1. And if you measure at the end which detector you landed at, you get 50-50. Does that make sense? Ask me any questions. So this is crucial. So Miles is happy with this. Zach, good? Mm-hmm. And Lorraine correctly points out that we're still setting off the firework part of the time. Yes, that's correct. Firework is an observer, Jacob, yes, absolutely. because it's making, remember what all that the observer was doing from an abstract point of view is making a measurement. The firework in that respect is no different than an observer. It's measuring whether the photon has gone below, in which case you'd see an explosion, or it's gone up, in which case there's no explosion. It's extracting this crucial bit of classical information, explosion or not explosion. That's why it's making a measurement. And so the really brilliant thing here is the following, right? Let me recap what we've seen so far. Exactly, Emily, yes. So to recap, in the case that the box was empty, no firework, remember there was interference. That was kind of like, if we make the analogy with a double slit experiment, that was kind of when you don't have any observer, you let the system evolve and you see interference. And the photon in that case always hits detector A. That's the case that we saw when no firework was present. And now just in the last slide, we saw that when the box contains the firework, 50% of the times the firework gets set off, too bad, right? And now the other 50% of the time, when the photon goes up and you don't explode the box, you're gonna detect, you're gonna hit detector A half of the time, right? You're gonna hit detector B half of the time, so total 25 and 25. So all in all, the conclusion is that if you observe the photon hitting detector B, you are sure that the box contained the firework, but crucially, you have not made it explode. This is the really big deal. When the photon hits detector B, we are certain that the box contains the firework, because in the case that there's no firework, you always go to A. So if you're hitting B, there must be a firework, but it has not exploded, right? We're in the case where the photon has taken the upper path. Okay, so all in all, we were able to, at least with partial success, you know, in a puzzle that seemed completely impossible to solve classically, right? Classically, there was no chance of knowing that the firework was in the box without setting it off. Here we have at least 25% chance of knowing for sure there is a firework without making it explode. Because if there's no firework, we see interference and you always go to A. If there is a firework, you would measure, but if you get lucky, you can sometimes detect it. So has this experiment been done or something similar to it? Yeah. I mean, this experiment is not difficult to do. Yeah, people can do this kind of experiments, and this is what you see. So it's actually quite nice. There have been times where you realize some observer you weren't previously aware of collapse your wave function. Absolutely, and that's actually a very serious problem for quantum computing, because so you know, ideally, right, you would want sort of your quantum states to only be measured whenever you want to. Unfortunately, there are many things that can accidentally observe your quantum states. Quantum states are very delicate. I mean, unless you're in a vacuum, you know, like any little sort of photon that shines at them, sort of any particle that sort of hits whatever you're using to create your quantum state could accidentally measure it. As in particular, if you're, you know, any particle of dust or anything really could accidentally measure it, unless you make sure that you're really in sort of close to a vacuum state, you're really close to absolute zero temperature. And this is the engineering challenge in building a quantum computer, is to make sure that your states are actually preserved. They don't get measured when you don't want to. This is called decoherence, this problem, when your states accidentally get measured. So a quantum state is a vector with complex entries. The quantum state of a qubit is a two-dimensional vector represented as follows. We're all clear on that. Equivalently as alpha 0 plus beta 1, where ket 0 and ket 1 are the standard basis vector. A quantum state evolves in one of two ways: via measurement, in which case you obey Born's rule, and the state after the measurement collapses to the observed measurement outcome, or via a unitary linear transformation, which is a multiplication by a unitary matrix. Born's rule, here's a recap, right? Alpha 0 plus beta 1, you would observe 0 and collapse to 0 with probability magnitude of alpha squared, and likewise for 1, it will be magnitude of beta squared. So this is all I have to say. I think we're already running very late, but I hope that this experiment was nice, that you liked it. And yeah, you should, you know, if it wasn't completely clear, you know, make sure that you go through this experiment again, make sense of it. I think it's well worth it.